Okay, so let's look at this puzzle. We had a set S of numbers, natural numbers that are both even and odd, and the question was, for all x in S, x does not divide x squared. Is it true? Is it false? How would you prove it? How would you disprove it? So here is a statement. So the first thing that you would notice is that there are no natural numbers that are both even and odd. So we are actually talking about for every x in, well, nothing, x does not divide x squared. Now things get puzzling and interesting. So, is this true or is this false? So let's, for simplicity, not to write too much, call x does not divide x squared p of x. If you want to say that it's false, if you want to disprove it, as I said before, we should give a counterexample. So we need an element in S such that x divides x squared. Well, can we find such an element in S? Can we find any element in S? There is nothing in S. So we cannot find such an element. We cannot find a counterexample. But how can we disprove it if we cannot find a counterexample? You know what? Maybe we cannot disprove it at all after all. So here's another way of looking at it. Maybe we could say that for every x in natural numbers, if x is an S, then x does not divide x squared. Okay, so now we are in a bit of a more familiar realm. We got an implication. In this implication, the left-hand side, x in S, is always false. No matter what natural number you take, it's not both even and odd. And what do we know about false? False implies whatever is true. So no matter what natural number x is, the statement, if x is an S, then x does not divide x squared, must be true. So surprisingly enough, even though x does not divide x squared, well, that just cannot possibly be true. The statement for every x in empty set, followed by really whatever you want to put there, is always going to be true, because you can never find a counterexample. You cannot disprove it. So such a statement for every x in knower p of x, some kind of formula, is called vacuously true. It's true, but not for a good reason. It's true just because there was nothing there to find a counterexample. So let's look at some inference rules that actually talk about things being there or things or all the things in a set. So the main inference rules that we are going to add, because we are working with quantifiers now, are the rules that allow us to strip the quantifiers from the formulas and put the quantifiers on the formulas. So the first rule is called instantiation. Instantiation means you remove a quantifier and instead you either put some specific element or just put an arbitrary element with some name. It really will be different for universal and existential, but the whole idea of instantiation is you go from, for every x, so there exists an x, to here is a specific x. We could call it a 2, we could call it a k, but that's something specific. And with that specific thing, we could say more than we could say about all the elements. If we have a specific k, we could talk about that k being even or being odd or being greater than 0. If we talk about all possible numbers. Well, some of them are even, some of them are odd, some of them are greater than 0, some of them are not. It makes it a little easier to reason about something if you're talking about one specific thing with a name. So the opposite of instantiation is generalization. That's when you didn't have a quantifier in the formula and you just had some free variables, or maybe specific constants there, well, free variables. And now we are putting a quantifier onto that formula, replacing that free variable or a constant. So here is an example. If you know that 2 is even, you could conclude that there is an even number. So you had a formula without quantifier, even of 2, and you got a formula with quantifier. There exists x, even of x. This is generalization. So think about instantiation as going into a forest and picking a specific tree, and generalization as moving away from the specific trees and applying what you learn about that tree to the whole forest. So let's do some examples. Let's start with existential generalization. This is when you start with something without quantifiers and you bring in an existential quantifier. And the general structure will be like this. If you could prove that the formula is true for some element A in a set S, then there exists an element in that set where the formula is true. If you think I'm just saying an obvious thing, yes, I'm saying something that's obvious, but I'm trying to say it mathematically. For example, as before, we know that 2 is an even number, therefore there is some even number. Well, that's 2. If we know that penguins don't fly, then there is some bird that doesn't fly. It's a counterexample to every bird flies. And we can apply that existential generalization rule more than once. For example, suppose we know that Jane loves Jim. First thing we can conclude, well, doesn't really matter in which order in this case, but we can conclude that somebody loves Jim. Well, that's Jane. And moreover, we could conclude that there are two people such that one of them loves the other. And the person who loves is Jane, and the person who is being loved is Jim. Back to our Valentine's Day stuff. So the other side of existential generalization is existential instantiation. That's when we have a formula with a quantifier and we get rid of this quantifier. A lot of time you don't know beforehand what exactly is that value of x, which is a witness for the quantifier. But you can give it a name. And once you give it a name, you could say, well, there is this thing, let me call it k, and I could say something about that k. Maybe I can figure out if it's odd or even. Maybe I could figure out something else. So here is a very typical example. Let n be an even number. Then n is equal to k for some k. Where is the existential instantiation here? Well, it's in saying that there is a number k, and we don't really need to compute it. We just need to give it a name, which is equal to half of the number n when n is an even number. So one caveat when you are doing existential instantiation, and we are going to do a lot of it because we are going to see over and over a definition of something which is of this form. An even number is a number that's 2 times something else. Or something is divisible by something when we could find a number that gives the first one when multiplied by the second, so on and so forth. So one thing to keep in mind is every time we are applying this rule, every time we are bringing in a name, we need to introduce a name that we haven't used before for anything else. So if we say Even number means there is some k such that my number even 2 times k. And now we want to say n and m are two even number. You might be tempted to say n equals to k and m equals to k. But wait a moment. If you say that, you just made n and m the same number, which is probably not what you intended. So instead, here you're applying the rule twice. First time you're applying it to n, and the second time you're applying it to m. And every time you apply the rule, you need to introduce a new name. Again, remember, the name is just a name. I could call the thing a k, I could call the thing an s, I could call the thing really whatever I want, as long as I don't call it something like for or person. And there is a lot of choice for different names to use. So every time you're doing existential instantiation, use a new variable, a new name to call whatever that thing was that was a witness, that existential witness for that existential statement. So let n and m be two even numbers, then n equals to k and m equals to l, whatever. N equals to s and m equals to t. So let's now look at universal side of things. In universal instantiation, again, you start with a formula with a quantifier, this time a universal quantifier, and we strip the quantifier and give it a name. But there is a big difference here. For the existential instantiation, we were given it a name saying, well, such a thing, the quantifier tells me that such a thing exists. I don't know what it is, so I call it a k. Here, we are allowed to put any element of S. Or we could also put a name, or we could put a specific element of S, because if it's true everywhere, well, it must be true for any specific element. So if for every natural number that number is greater than -1, we could take a number 5 and it will be greater than -1. We could take a number 100 and still will be greater than -1. That's because if the original formula is true, then the formula under the quantifier will be true no matter what natural number we will replace the x with. In the proof, though, you're not going to see that much of 5 is greater than equal to -1. In most cases, you're going to see something like, let A be an arbitrary element of S. Just giving it a name. But in this case, A can stand for any element of S, not just that specific element that must exist because of the existential quantifier. Then it allows us to look at that element S and say, well, it can be anything. It can be something greater than or equal to 0. It can be something less than 0. It can be something even, and can be something odd. And then we could talk about those cases separately, and in doing that, cover all the possibilities. So once we do this, starting with let A be an arbitrary element of S, if you prove that f of A is true without any assumptions about A other than that A is an S, then you can conclude that for every x, f of x is true. And this is the final rule, which is called universal generalization. Here's an example. So suppose we want to prove that for every x, even of x or odd of x. We could start with universal instantiation, saying let k be an arbitrary integer. Maybe this k is even, then the formula is true. Or maybe this k is odd, then the formula is still true. So the formula, either k is even, or k is even or k is odd, is going to be true no matter what k you pick. For arbitrary k, it's going to be true. Now that you proved it, you can conclude, because k was absolutely arbitrary, I assume nothing about it, I can conclude that for every integer, it's either even or odd. So now that we have this language of universal and existential instantiation generalization, let's go ahead and prove a little theorem. And again, as we're going over it, it's really not about what the theorem is saying, it's about the structure of the proof that we are trying to figure out. So remember, we looked at axioms and definitions of logic. So axioms say things like f, like something or something is the same thing as the or in the reverse order. Definitions would say things like A implies B is the same as not A or B. And we are going to use them now together with those rules about quantifiers to prove the following. For any propositional formula A and B, not B implies not A is the same as A implies B. Yes, we did talk about it before. We did say that contrapositive of an implication is equivalent to the implication itself. And I think we might have proved it by exhaustive method, by looking at the truth table. But here we are trying to prove the same thing in using a more general method, using something that can be applied not just to formulas where we could look at the truth table, but numbers and all sorts of other things. So our first line will be universal instantiation. We'll say let A and B be arbitrary formulas, propositional formulas. So A can be true, A can be false, B can be true, B can be false, arbitrary. So for those A and B, whatever they are, by definition of implication, not B implies not A is the same as not B or not A. Then we can apply double negation, another axiom. Then we can apply another axiom to switch the order of B with B and not A to get not A or B. And finally, we could use the definition of what it means to write F implies G, but now our F will be A and our B will be G. The first time we used the definition, our F was not B and our G was not A. So now, here's where we are. We took arbitrary A and B, and for those arbitrary A and B, the propositional formulas, we showed that not B implies not A is equivalent to A implies B. And we showed it by just using definitions and axioms of propositional logic. Because A and B were absolutely arbitrary, we didn't ever say, oh yeah, and A must be true or anything like that, or that A has to consist of that and that. We can conclude by universal generalization that for any A and B, not B implies not A is equivalent to A implies B.